They said it would disappear. 3i Atlas did not. It stayed. Its glow changed. Its speed changed. Its silence changed. On December 15, 2025, Earth and 3i Atlas will align in a way unseen in human records. Telescopes will watch. Signal monitors will listen. NASA calls it harmless. Some observers disagree. They think the object is waiting. The countdown is underway. Picture a clear October night. You stand outside and look up. Everything looks normal. Somewhere beyond your sight, an object from another star races toward an unscheduled meeting. NASA says relax. The ESA calls the approach routine. Amateur astronomers see odd behavior. We have seen 3 interstellar visitors. In 2017 came Oumuamua. It accelerated in ways gravity could not explain. In 2019 came Borisov. It looked like a comet but raised questions about composition and origin. Now comes 3i Atlas. It refuses to behave like a regular comet. Discovery came July 1, 2025. The Atlas telescope in Chile spotted a faint smudge moving against background stars. Orbit calculations showed a hyperbolic path. The object arrived from interstellar space. Speed approached 60 km per second, eccentricity exceeded 6. The path was extreme. Agencies published basic facts. Perihelion occurred near October 30 at about 1.36 to 1.4 astronomical units. The closest approach to Earth will fall in mid to late December near 1.6 to 1.8 astronomical units. Agencies called the distance safe. Amateur observers reported mismatches. Some measured position offsets of several arc-minutes from JPL predictions. Others recorded brightness patterns that did not follow models. Tail direction showed unexpected shifts. Those reports might be errors. They might be real. If real, even slight deviations could alter the December geometry. By December 15, the object will lie downstream of its wake. If the comet developed an ion tail or a cloud of charged dust, Earth will sit in the path. Radio signals would reach us in minutes. Charged particles could arrive in days or weeks. Even small electromagnetic disturbances could produce auroras at unusual latitudes or glitches in satellite telemetry. This is not an impact scenario. The object will be far too distant for that. The concern is subtler. A burst of radio waves. A sudden brightening. A glitch in satellites. Events small enough to dismiss as coincidence but odd enough to raise questions. Archive images reveal more. 3i Atlas showed activity far beyond Jupiter's orbit. It produced a coma near 6.5 astronomical units. Comets normally stay inert so far out. This object was active early. Hubble constrained the nucleus size between roughly 0.4 and 5.6 kilometers. Gemini confirmed the hyperbolic path and added polarimetric data. The coma produced extreme negative polarization. Dust properties appeared unusual. Amateur networks posted position and photometry data. Some reported systematic offsets. Multiple independent observers showed correlated displacements. That reduces the chance these reports are random noise. What could force a comet off course? Asymmetric outgassing is the standard explanation. Jets of escaping gas act like tiny thrusters. For the scale of offsets reported, the thrust would need to be unusually strong or persist in one direction. Other possibilities include plasma interactions with the solar wind, perturbations from unseen mass, or, less likely, an engineered propulsion signature. Official statements remain firm. 3i Atlas is a comet. Its trajectory poses no risk. Agencies have not posted daily position updates or extensive photometry. Silence allows suspicion to grow. Silence might mean caution. Silence might mean uncertainty. Think about the geometry. Perihelion passed near October 30th. By December 15th, the object sits roughly 1.6 to 1.8 astronomical units from both Sun and Earth. A line drawn from Sun through the object points almost directly at Earth. If the ion tail points away from the Sun, Earth lies in its path. What happens when Earth meets a stream of cometary ions? Earth's magnetosphere could couple with the incoming plasma. Magnetic reconnect ion could follow. Electric currents could flow in the upper atmosphere. We might see auroras and geomagnetic disturbances. Satellites could register anomalies. Ground systems might note oddities. Nothing planetary in scale, but noticeable. 5 thought experiments worth noting. Silent activation. Heating triggers an internal reaction that releases radiation or particles timed to arrive at Earth. Gravitational and plasma resonance. Tail structures interact with Earth's magnetosphere and amplify effects through resonance. Fragmentation and outgassing burst. The nucleus breaks and ejects dense clouds of debris that Earth crosses. Probe hypothesis. A small artificial device within the nucleus activates and transmits. Optical glint. Geometry causes a temporary spike in reflected sunlight, producing a sudden brightening. None of these break physics. Some are likelier than others. All remain possible until data rules them out. Institutional behavior matters. The response to Oumuamua taught agencies lessons about early announcements. With 3I Atlas, initial disclosure happened fast, but subsequent detail slowed. The difference fuels speculation. Maybe agencies act cautiously to avoid hype. Maybe they withhold while they sort anomalies. Either way, delayed transparency breeds doubt. History offers perspective. Oumuamua arrived without a coma and showed non-gravitational acceleration. Debate followed. Borisov behaved like a comet and fit expectations, but still surprised with composition differences and fragmentation. Each visitor showed diversity. Each forced humility. Amateur astronomers play a growing role. They bring time and dedication. They share raw data online. Their position measurements have larger uncertainties than professional observatories. Still, repeated independent reports from varied setups carry weight. Collaborations between professionals and amateurs could resolve anomalies fast. Forces at play include gravity, radiation pressure, solar wind, and electromagnetic interactions. Outgassing thrust is well known. Small accelerations add up over weeks. Plasma and magnetic structures shape ion tails and can create complex tail geometry. Hidden masses would perturb orbits only if substantial or close. The simplest explanation remains asymmetric outgassing, but we must keep options open while data accumulates. SETI researchers watch, too. A deliberately timed transmission during alignment would be efficient. A reflector concept would let a distant transmitter bounce a signal off an interstellar object to reduce transmission power. Both ideas are speculative engineering, not wild fantasy. Machine learning changes discovery. Large surveys and anomaly detectors flag unexpected behavior. Algorithms trained on known comet behavior will raise alerts for unusual light curves, tail shifts, or positional trends. Humans must vet those alerts. False positives happen. Still, matched flags across independent systems would strengthen the case for follow-up. Planetary defense protocols focus on impact risk. 3I Atlas is not an impact threat. Yet unusual behavior raises the question of watch lists and disclosure. Watch lists exist for training and protocol testing. Inclusion on internal lists does not mean public danger. But secrecy fuels rumors. Agencies face a trade-off between public clarity and scientific caution. Space weather complicates analysis. Solar flares and coronal mass ejections produce geomagnetic storms. In an active solar cycle, timing overlaps are plausible. If a solar storm and a cometary outflow reach Earth together, disentangling sources will be difficult. Composition measurements from upstream spacecraft would help. Most available probes measure bulk properties, not detailed cometary composition. A cometary signature might go unnoticed. Fast radio bursts add another layer. FRBs occur daily. A burst whose arrival direction aligns with 3I Atlas during the December alignment would be unlikely but not impossible. Radio signals from cometary plasma are another possibility. Detection requires radio telescopes pointed at the right spot at the right time. Speculation can motivate such observations. At core sits the Fermi paradox. The galaxy teems with stars and planets. Life seems probable by numbers alone. Silence persists. Interstellar objects offer a test of one hypothesis: probes or reflectors as communication methods. 3I Atlas provides another chance to test that idea. Most likely outcome: December 15th passes with no dramatic event. The object behaves within updated models. Minor anomalies would spark debate and papers. A clear artificial signal is the least likely outcome but the one with the largest impact. What you can watch. Know our space weather feed for geomagnetic indices and alerts. JPL Horizons for position updates. Amateur astronomy forums for shared astrometry and photometry. SETI and radio observatory bulletins for transient reports. News and verified social channels for official statements. If you follow the data, you help track reality instead of rumor. Observe with skepticism and curiosity. Record results. Share measurements. 3I Atlas is likely rock and ice from another star. It carries chemical clues about its origin. That alone matters. If it turns out to be more, the implications will reshape science and culture. Either result moves knowledge forward. The vigil has begun. Telescopes are trained. Satellites monitor space weather. Amateur observers stand ready. Whether the sky remains silent or offers a signal, your attention matters. Look up. Watch. Record. The countdown continues. Around the world, telescopes turn to one small patch of sky. 3I Atlas drifts there, cold and fast, a visitor from another star. Professionals track it through automated systems. Amateurs sit under the night sky with cameras and scopes, comparing data in real time. News feeds refresh every minute. Forums hum with speculation. Most expect nothing. A few expect everything. If a geomagnetic spike appears, it will show first in NOAA's K-index. If auroras reach lower latitudes, photographers will catch them within hours. If satellites report signal noise or orientation glitches, agencies will flag it as space weather. If radio telescopes detect a pulse, SETI dashboards will light up. Everything depends on measurement. Most signals will have normal causes. Solar wind, background noise, calibration drift. But one clean anomaly would change everything. A pattern in the static. A pulse that repeats. A deviation too large for physics as we know it. That's the edge everyone watches for. Even silence tells a story. If December 15th passes without noise, the models hold. 3I Atlas becomes another natural traveler, a frozen messenger from elsewhere, obeying physics but carrying mystery. Scientists will write papers. They'll refine models of comet dynamics, plasma tails, and non-gravitational acceleration. They'll archive the data and move on. But the watchers will remember. They'll remember the night the world looked up together, waiting to see if the sky would speak. The lesson doesn't depend on what happens. If the object behaves exactly as predicted, that's knowledge gained. If something deviates, that's knowledge gained too. Either way, it shows that the act of watching matters. The bigger question never changes: are we alone? 3i Atlas is one answer in a long chain of questions. Oumuamua started it. Borisov continued it. Now Atlas gives us another chance to learn how interstellar objects behave and what they carry. Maybe someday we'll find one that leaves no doubt. A signal, an artifact, a deliberate pattern. Until then, we watch. We measure. We question. That's what defines us. If you want to witness this moment, follow the data feeds on December 15th. Look up when the sky is clear. Remember what you're seeing: light reflected from an object that came from another star system, crossing ours for the briefest time before it vanishes again into the dark. After that, it will fade. The numbers will settle. The reports will quiet down. But the question will remain, waiting for the next visitor. Because there will be another. And when it comes, someone will remember this date, this countdown, this shared vigil. 3i Atlas is the rehearsal. The next one could be the message. Weeks pass after December 15th. No explosion. No radio burst. No visible anomaly. 3i Atlas keeps moving, a dim, fading trace against the stars. The world exhales. Headlines fade. The object becomes background. Yet astronomers still sift through the data. Petabytes of telescope logs, magnetic readings, and sky maps. Every chart gets cross-checked. Every outlier examined. Tiny irregularities surface. A faint brightness fluctuation. A minor delay in solar wind readings. A momentary distortion in one deep space relay. Nothing conclusive, but not all noise either. Papers appear in small journals. Possible photometric deviations in 3i Atlas. Statistical review of ion tail alignment events. Quiet science, cautious words, uncertain conclusions. The kind of work that builds understanding one decimal at a time. For most people, the story is over. For the watchers, it isn't. They remember how the numbers almost lined up, how the geometry felt too perfect. They keep an eye on the next catalog release, waiting for another interstellar entry. By spring 2026, 3i Atlas has left the solar system. Its light is too faint for ground-based telescopes. Its orbit is logged, archived, and left to math. 60,000 years from now, it will cross another system, maybe one that's ready to notice. Back on Earth, something lingers. A subtle shift in how people think about the sky. Astronomy forums stay crowded. New amateur observatories open. High school students build tracking software in their spare time. Someone starts a project called Interstellar Watch, combining public telescope data with machine learning models to flag new anomalies automatically. The interest never fully dies. Every small comet discovery now sparks the same question: interstellar or local? Every data release carries a faint echo of that countdown. Maybe the silence of December 15th was the message itself. A reminder that the universe does not perform on demand. That our curiosity matters more than confirmation. That the act of looking up connects us, even when the sky says nothing. 3i Atlas came and went. It didn't speak, but it made us listen. And maybe that's the point. Because the next one is already out there, inbound through the dark. Invisible for now. Waiting for its own moment of alignment. And when it appears, we'll be ready again, eyes up, data streaming, the world holding its breath. The countdown never really ends. Months turn into a year. The night of December 15th, 2025, becomes a footnote in most news archives. Comet from another star passes safely, no anomalies detected. But inside observatories, the story never quite closed. 3I Atlas left behind more questions than it answered. Teams at NASA, the European Space Agency, and the Rubin Observatory quietly continue comparing datasets. Magnetometer readings, solar wind data, brightness curves, and telemetry logs are merged into massive timelines. No single anomaly stands out. Yet something subtle appears in the correlation graphs: weak, repeating fluctuations that don't match normal solar wind noise. The variations are small, buried in noise, but statistically consistent across multiple instruments. Too small to prove anything. Too regular to ignore. A few researchers propose a term: microresonance events. Tiny disturbances in plasma density possibly linked to the comet's passage. The idea doesn't make headlines. It barely makes it out of peer review. But it sparks debate inside the scientific community. If a comet from another star could create measurable effects across millions of kilometers, what does that say about interstellar dust, plasma, or structure? Meanwhile, the amateur community stays active. Thousands of small telescopes keep feeding data into public networks. Every object tracked, every reading stored. The old excitement has turned into quiet persistence. People are watching not for spectacle, but for pattern. By mid-2026, new data emerges from deep space probes. Voyager 2's plasma instrument, decades old but still running, records a slight density rise in interstellar medium readings around late January. Nothing major, but when plotted against 3I Atlas's trajectory, it lines up. The signal delay matches travel time for a charged particle wave moving outward from the inner system. Coincidence? Maybe. But the math fits almost too neatly. NASA's internal memo reads, insufficient data for interpretation. Possible residual interaction from solar activity or cometary plasma dispersal. No further comment. In early 2027, another object enters the discussion. A new detection, faint and fast. Preliminary orbital solutions suggest a hyperbolic path, another interstellar arrival. It's smaller than 3I Atlas, dimmer, harder to track. But for the small global network of watchers who remember that December night, this is the signal to return. They call the new one Helios trace. This time, protocols are different. Data is shared in real time. Public dashboards map the trajectory hour by hour. Machine learning tools built after Atlas are already analyzing incoming images. They flag anomalies instantly. Astronomers who dismissed the Atlas discussions 2 years ago now join the effort. There's no stigma left in paying attention. The first weeks of tracking Helios trace confirm its interstellar origin. Its velocity is even higher than Atlas's, 92 km per second. Its light curve is stable but polarized strangely. That word again, strangely. A subtle reminder of how little we understand about these travelers. The public takes notice again. Documentaries replay the story of Atlas. Clips from December 2025 trend again, people looking up, scientists speculating, the collective anticipation of that night. In hindsight, the event feels almost historic, not because of what happened, but because of what it started. Back in 2026, one of the lingering mysteries of Atlas comes back to life. A grad student at Kyoto University reanalyzes archived photometry using a new denoising algorithm. He finds faint periodic dimming in the light curve, tiny pulses repeating every 11.6 hours. The pattern could match the object's rotation, but the amplitude is too uniform. He writes a short paper, Possible Periodic Photometric Modulation in 3I Atlas. It circulates quietly online. A month later, a researcher at the University of Arizona compares that pattern to magnetic field fluctuations recorded by the ACE satellite during the same window. The peaks align within hours. The chance of coincidence is low, but still within plausible range. The paper ends with one sentence: if causal, this would imply a structured emission or reflection pattern from the comet's surface. No one uses the word signal. Not yet. Public attention returns briefly in December 2027, the second anniversary of the alignment. Several astronomy channels revisit the Atlas phenomenon. They stream timelines, raw data, and interviews with observers who were there. Some treat it as science history. Others frame it as unfinished business. One channel releases a 12-minute video titled "The Visitor That Made Us Look Up." It goes viral again. People remember that night not for what it proved, but for the feeling of connection. For a few days in 2025, everyone was looking at the same patch of sky, waiting for something bigger than themselves. By 2028, the community has matured into something new, a fusion of professional astronomy, citizen science, and automated AI observation. Hundreds of small observatories around the world form a synchronized array, feeding into an open-source network. They call it the Interstellar Watch Grid. Every image, every light curve, every magnetometer reading is shared instantly. Algorithms flag patterns humans might miss. When one node detects an anomaly, the others verify it within hours. It's science without borders, born from curiosity rather than hierarchy. The seed was December 15, 2025. NASA eventually releases a full retrospective on 3I Atlas. A quiet, technical report. No artificial activity detected. No measurable impact on Earth's magnetic field. No confirmed radio anomalies. But one paragraph draws attention. The observed polarization of 3I Atlas dust remains inconsistent with standard cometary models. Further study of interstellar dust composition and structure is recommended. For many, that's enough. A small mystery left open. A reason to keep watching. By 2030, the first dedicated interstellar object interceptor mission is under development. The idea: launch a probe capable of rapid acceleration to intercept the next confirmed visitor within months of detection. The mission name: Sentinel-I. Its secondary designation, unofficial, used by engineers, is Atlas's answer. 3I Atlas is now far beyond the heliosphere, moving through cold space toward nothing in particular. It leaves behind no trace, no wake, no message. Yet its brief visit reshaped how humanity watches the sky. It didn't bring contact or catastrophe. It brought awareness. A global realization that visitors come and go, and that each one could carry a story older than Earth. Years later, historians describe December 15, 2025, not as an event, but as a beginning. The night when the border between science and wonder blurred, and stayed that way. The observers who were children then are astronomers now. The amateurs who stayed up all night now run the public networks. The phrase Atlas alignment becomes a shorthand for human curiosity, a symbol for the moment we chose to look up together. When people ask what we found, the answer is simple. We didn't find aliens. We didn't find danger. We found a reason to pay attention. And maybe that's enough. If you stand outside on a clear December night and look toward the ecliptic, you won't see 3I Atlas. But somewhere out there, in the deep dark between the stars, it's still moving, a fragment of another world carrying silent data in its frozen dust. It doesn't know it changed us. But it did. Because since that night, we've been listening harder, watching closer, and asking better questions. That's the quiet legacy of 3I Atlas. Not revelation. Not fear. Attention. The countdown never truly ended. It only changed targets. The next visitor will arrive someday, and when it does, we'll be ready, instruments calibrated, algorithms waiting, eyes open. The universe speaks rarely, but it never stops moving. And every traveler through the solar system is a chance to hear a whisper from the stars. 8 years after the alignment, 3I Atlas has become legend inside the science community and myth outside it. Students entering astronomy programs know the story before they touch a telescope. Documentaries call it the night the world watched the sky. In classrooms, professors use it to teach orbital dynamics, public communication, and scientific humility. Yet research continues quietly. The data archives from 2025 are still being mined by new algorithms that didn't exist back then. AI models trained on a decade of comet observations run simulations thousands of times faster than humans ever could. They find patterns buried deep in the noise, subtle correlations between tail orientation, polarization shifts, and solar wind data. Each one small, each one statistically real. None large enough to rewrite the story. Together, they form a whisper that scientists can't explain. At conferences, sessions about interstellar object dynamics are standing room only. The talk titles are cautious but curious. Nonlinear plasma coupling in hyperbolic visitors. Possible early activity mechanisms beyond the frost line. The words 3I Atlas never leave the program, but everyone knows that's what they're talking about. The Interstellar Watch Grid has grown into a permanent network. Over 500 observatories, both professional and amateur, contribute data in real time. Every night, the system scans for fast movers, cross-references them with known catalogs, and sends alerts if something looks hyperbolic. Each alert triggers a cascade, satellite coordination, spectral requests, public dashboards lighting up. No object passes unnoticed anymore. The grid's founders still meet every December 15th. Not to expect miracles, but to remember why they built it. They gather online, share images, compare new data, and tell stories from that first vigil. Some have grown older, others were children then, inspired by that night. For them, watching the sky has become routine, a quiet form of devotion. In 2034, a signal surprises everyone. Not a transmission, not proof of intelligence, just an unexpected echo. A radio array in Australia records a brief, repeating reflection while scanning an outbound probe. At first, engineers think it's interference. But the frequency drift matches the Doppler profile of something roughly 60 km per second, far beyond any human craft. A quick search in the catalog shows a match. Trajectory consistent with an object that left the inner system in 2026, 3I Atlas. The reflection is weak, only a few microseconds long, repeating every few minutes before fading. Analysis shows it's not a transmission. It's the probe's own signal bouncing faintly off something reflective and distant, probably metallic dust or frozen crystalline ice in the comet's wake. Still, it sends a ripple through the community. 3I Atlas, 8 years gone, leaving a signature strong enough to bounce radar from Earth's side of the galaxy. The first measurable trace of its passage through interstellar space. A new mission forms around it. Engineers propose a high-gain radar array positioned beyond Mars to monitor deep reflections. They call the plan Echo Line. The goal is simple: when the next interstellar visitor passes, we'll bounce signals off it deliberately, not by accident. Atlas taught them the need for readiness. Echo Line makes it possible. By 2036, another visitor arrives. Designation: 4I Kepri. Detected earlier and tracked longer than any before. Within weeks, scientists know it's active even farther from the Sun than Atlas was. The same question rises: why so early? The same tension follows: what's natural, what's not, what's known? Public reaction is calmer this time. People have context now. They know that interstellar visitor doesn't mean incoming disaster. It means data, learning, shared wonder. The media still runs dramatic headlines, but the tone is different. Measured. Focused. On December 15th of that year, 10 years to the day since Atlas's alignment, observers mark the anniversary with the first coordinated Interstellar Observation Festival. Over 1 million people tune in to live feeds from telescopes across the world. Children watch streaks of light from backyard setups. Scientists narrate orbital simulations in real time. Every continent has eyes on the same sky. No anomalies occur. But the sense of connection feels identical to 2025. The event becomes annual. Each December, people remember the night the world waited together. Atlas has become a tradition. Science keeps digging. By the late 2030s, analysis of interstellar dust collected by high-altitude balloons shows a chemical signature never seen before, a mix of complex carbon compounds and trace elements matching the composition estimated for Atlas's Comet. It's not alien technology. It's chemistry older than the Sun. Evidence that the building blocks of life drift freely between stars. One research paper calls it panstellar organics. Another calls it Atlas dust. The name sticks. Soon after, textbooks update. A new section appears in planetary science chapters, interstellar cometary chemistry and cross-system transfer. For the first time, the idea that life's ingredients might travel between star systems is mainstream science, not speculation. Atlas didn't bring proof of intelligence. It brought proof of connection. A decade later, 2045, a museum opens in Chile near the site of the original Atlas telescope. It's called the Visitor Center. Inside, a wall-length mural shows the orbit of Atlas curving through the solar system and back into deep space. Interactive displays let visitors replay the 2025 alignment using real data. On a screen near the exit, a live feed from the Interstellar Watch grid scrolls new detections in real time. Every few weeks, another faint dot joins the list, 5i, 6i, 7i, each one tracked, catalogued, studied. School groups visit daily. Children look up at the mural, tracing the white line that represents Atlas's flight. Guides tell them the same story in simple words. This was the moment we decided to keep looking. Scientists still argue over details: how early activity starts, why dust polarization is extreme, why some trajectories drift by microfractions beyond gravitational prediction. They debate models late into conferences, not because they fear what they don't know, but because they're finally comfortable admitting it. Atlas made that acceptable. By now, space policy has changed too. The Planetary Defense Coordination Office has expanded into a broader mandate: Cosmic Observation and Response Division. It monitors asteroids, comets, solar storms, and now interstellar objects. When a new visitor enters the system, data goes public within hours. There's no silence, no secrecy. Transparency became policy because of Atlas. In 2050, long after most have stopped checking the old feeds, the Echoline Array detects another reflection. This one's stronger, clearer, longer. It lasts almost 10 seconds before fading into noise. Direction: the same patch of interstellar space where Atlas was last tracked. No one claims alien contact. The official explanation is plausible: dense debris, perhaps frozen metallic gas compressed into reflective sheets. Still, the timing feels poetic. 25 years after discovery, the first visitor to make humanity look up answers back, faintly, with a reflection of our own making. The data becomes public instantly. No controversy, no panic. Only awe. The world watches the waveform plot flatten into silence. Commentators call it Atlas's echo. Years later, when people talk about the event, they don't mention fear or mystery. They talk about participation. They talk about how it felt to belong to something larger than any country or belief. How billions of people shared a single point of focus for one night and realized they lived under the same sky. 3i Atlas is gone, but its shadow runs through every discovery since. It redefined what observation means. It taught science to be open and people to be patient. It turned the act of watching the sky into a collective ritual of curiosity. Every December 15th, the world still looks up, not out of expectation, but out of respect. Out of memory. Out of quiet hope that one day, among the countless rocks and ices drifting between stars, one will bring an unmistakable reply. Until then, we keep watching. Because that's what Atlas taught us. That even silence has value. That the search is the message. And that the universe speaks most clearly when we decide to listen. 3I Atlas is 25 billion kilometers away now, a cold ember sliding through the dark between the stars. Its light is gone from every telescope. No instrument on Earth can see it anymore, but its name still sits in the metadata of 1,000 research projects. Every new interstellar detection paper includes the same line near the top: method adapted from Atlas-era protocols. The object that once seemed like a mystery has become a reference standard. Scientists use it to calibrate new instruments. Students write simulation code that starts with its orbital parameters. The comet that changed nothing and everything is now a foundation. 1. The age of constant watching. The interstellar watch grid has expanded into orbit. By 2055 it includes 2 lunar observatories, 6 deep space telescopes positioned at Lagrange points, and hundreds of ground units. Every observation streams into a single global database. No borders, no paywalls. Raw data belongs to everyone. When a new object enters the solar system, an alert flashes on public dashboards. You can open it on your phone: a line of numbers, coordinates, a timestamp, and a blinking label: potential interstellar origin, verification pending. Children learn to read those alerts before they learn constellations. The night sky has become participatory. Observation is a civic habit, like voting or weather reports. People talk about magnitude and eccentricity in the same tone they once reserved for sports scores. 2. The long tail of Atlas. In the archives, teams still analyze Atlas data with new tools. A 2053 machine learning reanalysis of solar wind correlations finds something strange. A persistent modulation in particle density, repeating roughly every 11 hours, the same period hinted at by the 2026 re-examination of Atlas photometry. No one can say whether it's artifact or physics. The papers stay cautious. Still, every new Comet light curve model includes a parameter called a term, named quietly after Atlas. Another group studies plasma turbulence from 2025 to 2026 and notices that several faint radio emissions detected by the old Deep Space Network align in frequency drift with Atlas's position during its outbound leg. No pattern, no message, just a curious resonance that shouldn't have lasted as long as it did. They call it a cometary wake phenomenon. Others call it the Atlas hum. No one agrees, but no one dismisses it either. 3. The Watchers. The original Atlas community still exists. They call themselves Continuum. Some are professional astronomers. Most are amateurs who never stopped logging sky data. They meet online every month, trading measurements, debugging code, sharing rumors of the next detection. The group's motto is simple: keep the record. Every December 15th they hold a 24-hour stream. They replay the original data feed from 2025, synchronized with live sky views from around the world. The stream rarely spikes in viewership anymore, but it never goes dark. They say it's not about waiting for proof, it's about maintaining the habit of attention. 4. New visitors. Interstellar objects are no longer rare. By 2055, astronomers have catalogued 23 confirmed and 12 probable visitors. Each carries a unique signature, some dusty, some metallic, one that behaves like a loosely bound cluster rather than a single nucleus. They've stopped numbering them in Roman numerals. Now they use names chosen by global vote through the watch grid interface. 4i Kepri, 5i Tessis, 6i Orenda, 7i Halim. Every new detection starts the same cycle: excitement, observation, quiet study, archive. The system works. No hysteria, no secrecy. Atlas taught transparency. Among them, one object, 9i EOS, draws attention. It's large, bright, with a smooth rotation curve and faint periodic radio emissions. Not structured signals, just rhythmic bursts consistent with electrostatic discharges. Still, the public nicknames it the drummer. Media call it the first talkative rock. No one suggests intelligence anymore. The conversation matured. But people feel the old thrill again. They remember the first vigil. 5. The human echo. Atlas's greatest legacy isn't technological, it's cultural. Before 2025, space was a specialist's domain. After Atlas, observation became collective. Neighborhood observatories, balcony spectrographs, cloud-linked telescopes in deserts and on rooftops, all part of the same network. Children in Lagos, Mumbai, Sao Paulo, and Reykjavik grow up submitting nightly sky logs to the grid. Their software corrects for clouds and light pollution automatically. Every submission earns a small credit toward telescope time or access to the virtual planetarium. Astronomy becomes a shared commons, like the internet once was. Even art changes. Painters depict faint streaks across star fields labeled with orbital data. Composers sample the radio hiss of comets. A poet in Kyoto wins awards for a long verse cycle titled Atlas Alignment, written entirely in single-sentence stanzas. 6. The mission that chased a ghost. Sentinel-I, launched in 2030, never reached any target. It was a proof of concept. But its successor, Sentinel-3, launched in 2042, is operational now. It waits in standby orbit near Jupiter, fueled and ready to intercept the next object within days of discovery. Atlas made that mission inevitable. In mid-2056 the alert comes: an incoming body, high velocity, inbound from the direction of Lyra. Designation 12i Pele. Trajectory set for a perihelion close enough for interception. Within a week, Sentinel-3 fires its engines. For the first time in human history, a probe will meet an interstellar visitor face to face. As it travels, global attention returns. News feeds revive the old phrase, the vigil. Children born decades after Atlas learn the story overnight. They download live telemetry apps. Everyone watches together again. When Sentinel-3 arrives, the world stops. The probe's cameras show an irregular, metallic gray surface, rough but strangely reflective. Spectrometers detect complex organics frozen in the crust. Not technology, chemistry. But inside those molecules, isotopic ratios never seen in the solar system. Proof that the raw materials of life exist everywhere. Headlines call it the Atlas answer. No messages. No signals. Just connection. 7. The quiet revolution. After Sentinel-3, planetary science transforms. Every interstellar object becomes a target for sampling missions. The global space agencies form a single coordination group, COSNET, the Cosmic Network for Extrastellar Tracking. They share funding, instruments, and time. Competition fades. Discovery becomes cooperative. Meanwhile, AI observation evolves further. Neural observatories monitor the sky continuously, predicting not just where to look but when anomalies might appear. They forecast probability zones for unexpected behavior, a kind of cosmic weather report. Atlas data trained the first of these models. Public interfaces show these predictions as heat maps overlaying the night sky. People check them like aurora forecasts. Sometimes nothing happens. Sometimes a small flash, a micrometeor, a comet outburst. But people keep checking. The habit persists. 8. Memory and meaning. By 2060, the anniversary of the alignment becomes an international observance. Not a holiday, but a moment of shared reflection. Schools shut lights for 1 hour. Cities dim billboards. People look up. The act is simple. Remember the night when humanity paid attention together. Museums hold exhibitions of early atlas data. Visitors can scroll through original observation logs, the tiny fluctuations that once meant everything to those who watched. Children press buttons that replay real telescope sounds, faint static, the heartbeat of light. They learn how silence can carry meaning. Older scientists walk among them quietly. They know the world changed not because of what was found, but because people learned to listen. 9. The far future signal. In 2064, a faint transmission arrives at Earth from the outer solar system, barely detectable above noise. Not a message, just a long, thin echo at frequencies close to those used in the old Deep Space Network. Triangulation suggests the reflection came from roughly the region where Atlas would now be, give or take several light hours. The signal repeats once, then stops. Engineers confirm it's likely a reflection of a burst from one of the newer probes. Still, the symbolism isn't lost. The news headline writes itself. Atlas replies, sort of. For a few days, the world remembers again. Not because anyone believes it's intelligent, but because it feels poetic. The first interstellar traveler we truly watched still mirrors us, even from the dark. 10. The long horizon. By the late 2060s, humankind lives in the era Atlas began. Space is mapped not as territory but as network. Each object, each dust cloud, each distant signal sits in context, catalogued, cross-referenced, understood through shared data. The line between professional and amateur science has disappeared. Everyone who looks up is part of the system. The phrase "the Atlas Protocols" enters law. Open data, early disclosure, coordinated response, global access. Every agency follows it by default. No discovery belongs to one nation anymore. When new civilizations begin their own space age centuries from now, they might find one of our probes and read its inscription, "We watched because we could." 11. The quiet sky. At the midpoint of the century, most people born after the event have never seen a night sky without satellites. But once a year, on the alignment night, every participating nation turns off non-essential satellites for 2 hours. A brief window of darkness. You can look up and see the Milky Way again, unbroken. In that moment, billions remember a comet that came and went and somehow rewrote how we see ourselves. 3i Atlas keeps traveling. It will not return. It will never know the attention it inspired. But its legacy endures in the eyes that still watch, in the instruments that still listen, in the silence that still teaches. Because the greatest discovery was not out there at all. It was the realization that looking together, carefully, patiently, honestly, is the closest thing we have to contact. The universe hasn't answered yet. But we learned how to listen. And sometimes, that's the first word of a conversation that hasn't begun.